Harry will introduce you right now.
You want me to start? All right. Good afternoon. I hope you had a good lunch. I understand it's quite hot there. We're warm here in Houston, kind of most of the time, but it's unusually warm today. I think it's about 25 degrees Celsius, and we're in the middle of winter. So today I'm going to continue in lecture 2 to talk about quantum magnetism, which I think is a good example of quantum simulation using ultra-cold atoms and really exploiting the ability to tune parameters and to have very clean representations of model Hamiltonian. This is true both with what I'll talk about in terms of quantum magnetism, but also in the second subject, which is tomorrow, which is fermions in one dimension. All right, so let me acknowledge people who did the work. This was done by experimentally by Pedro Duarte, Russell Hart, and Sung Lin Yang. And we had some great collaborations with David Hughes, Teresa Paiva, who I know is a speaker at this summer school, Asan Katami, Richard Skolatar, and Nandini Trivedi. So we talked last time about composite bosons on the left and composite fermions on the right. And of course, lithium-6, because it consists of an integer number of, half-integer number of bosons, an odd number of bosons, I should say, an odd number of fermions, I hope to say. It is itself a composite fermion. And so the lithium-6 rather than lithium-7 will be the subject of our experiments and what I'm going to talk about in the next 50 minutes. So bosons and fermions are different, but only when you get low enough into this quantum regime that I discussed last time, low enough temperature. So if you look on the left of this figure, I show an image of a density profile of lithium-7 atoms coexisting in a trap with lithium-6 atoms, which are on the right. And the temperature here is about 800 nanokelvin. And it turns out that that temperature is about equal to the Fermi temperature. And I defined the Fermi temperature on the previous slide and also earlier this morning to be the energy of the last occupied level of the confining potential. So the bosons and the fermions are essentially identical in this regime where the temperatures are above the degeneracy point. But as you go to lower temperatures, you begin to see that the fermions require more space than do the bosons. And this is a temperature now, which is about a half of TF, half of the Fermi temperature. And in that at that temperature and below, the quantum statistics really begin to manifest themselves. And one can see differences that are even bigger at a quarter of the Fermi temperature, where it's very clear now to see that the fermions do in fact require more space than the bosons. The density is more spread out in the case of the fermions. And this is true even if you go to zero temperature. So I'm showing here the size of the gas, the trapped gas, as of lithium-6, the Fermi gas, as a function of T over TF. And the yellow data points are the data. And the green line is the high temperature maximal Boltzmann statistics limit, where you see that even as, if you go all the way to T equals 0, the size of the cloud should, according to the high temperature statistics, not deviate. But of course, Fermi Dirac statistics, they do. And they never can get below, even at T equals 0, there's a finite energy and a finite pressure that stabilizes this kind of like a white dwarf star that was first proposed by Enrico Fermi in 1926. So in 1926, he showed that the Fermi energy was proportional to the density of the 2/3, and that there was an equivalent pressure. He didn't call it a Fermi pressure, but there is what we now call a Fermi pressure, which is purely due to quantum degenerate effects, quantum degeneracy. And the pressure is finite even at t equals 0. So you can see this function as a constant part and another correction, which is due to the statistics. So this Fermi pressure is what stabilizes white dwarf stars against gravitational collapse. So as long as the mass of the star doesn't exceed the limit, the Chandrasekhar limit, the star should be stabilized by this quantum degeneracy. Because of the Pauli exclusion principle, the electrons in the white dwarf star cannot overlap each other. All right, so we talked a little bit earlier about many-body physics with ultra-cold atoms, and the real power of cold atoms for quantum simulation is the ability to attune a rather clean system, very well-known set of parameters that can be tuned. For example, interactions via the Feshbach resonance, which we talked about earlier, lattice hopping and temperature and so on. And I went through this list before. So these are various geometries of optical lattices from 1D to 3D. And for tomorrow's talk, this configuration will be of particular relevance. So this is our target. This is a phase diagram of a generic high temperature superconductor. Happens to be a cuprate superconductor, but this is really very universal. The numbers will be different on the axes, but essentially all non-conventional superconductors have this similar phase diagram, in that there is at low particle doping or hole doping. This is n equals 1. There's 1 electron per site. That site becomes a mod insulator, and then an antiferromagnetic mod insulator at temperatures below what's called the Néel transition temperature. So in this green region, you expect to see antiferromagnetic correlations where there is an alternating, in the classical sense, an alternating up-down spin projection in this antiferromagnetic undoped region of the phase diagram. But if you go very much colder than the Néel transition, and where the lattice is doped, and what doped means is that you add extra electrons or extra holes. In this case, it's hole dope, and it corresponds essentially in cold atoms to changing the density. So this, you can think of this axis as density. This is a density of 1 atom per site, and this is a higher density of electrons or holes. So this blue region is the region that is particularly interesting. It's the D-wave superconducting region, and there might be a quantum critical point where a quantum phase transition can occur. And then there's some other interesting regions of this phase diagram, even at higher temperatures, that people don't quite know what to make of. One called the pseudogap or preformed pair region. And this is T star is not really a phase transition, but rather some kind of a crossover between a mean field like Fermi liquid into the pseudogap region. So the point is that there's some very interesting physics going on with these high temperature superconducting materials, and we don't know very much about them, or we don't know as much about these materials as we would like. I think that's a fair statement. And so we had set about trying to understand these phases better. And the first thing that you'd like to look at is this region where the correlations are antiferromagnetic. This is occurring at the highest temperature. And so we have a better chance of accessing that region experimentally. So for these cuprate materials, Fermi temperatures of order 10,000 degrees Kelvin. So this Néel transition, even though it's above room temperature in most cases, is still quite low relative to TF. And this is important to note because the difficulty in doing experiments increases not with absolute temperature in this field, but rather the relative temperature relative to the Fermi temperature. So I'm going to first talk a little bit about optical lattices and the Hubbard model, and then we'll talk about mod insulator and how to detect antiferromagnetic order in the mod insulating phase. All right, so an optical lattice or any kind of optical trap depends on this optical forces and optical potential, which is induced by tuning a very high-powered laser near some resonance, or even in most cases not that near in resonance. But the detuning condition is that this frequency, the detuning delta corresponds to the frequency difference between the laser frequency and the transition frequency to some excited state. And when that detuning is red, meaning the laser photons are less energetic than this transition energy, then one finds a minimum in light potential energy. And you can make a trap where the atoms congregate around the highest intensity regions of the focused beam. And that's called an optical dipole trap. And it's made famous originally by Steve Chu, and it was at least part of his Nobel Prize in the early 90s for laser cooling and trapping. Now, so such a scheme that Steve invented was to, and Art Ashken as well, is to make a focused laser beam with high intensity, detune the laser beam to red of some optical transition, maybe 100 nanometers to the red by a lot in terms of wavelength. And because this high intensity focused region is lowest in energy, the atoms like to be trapped there. And this is a really flexible way of making forces using optical, high intensity optical lasers. So this is how one can make a standing wave. To make a standing wave, you just simply retro reflect one laser beam on top of another one. This is a mirror and this is a lens. And so that it focuses back on itself and creates an interference pattern, which are bright, dark fringes. And again, if your laser is red detuned, the atoms like to congregate in these bright regions. And that's, in fact, all there is to an optical lattice. That's just a one-dimensional optical lattice, but it gives us an idea that of the relative simplicity of making these kinds of lattice structures and the flexibility we have in focusing and manipulating laser beams to give us different geometric patterns in this interfering light waves. So here's an example where you have three of these single dimension optical lattices, and you superpose them together on one region of space. And you can imagine then you create an array, a cubic array of atoms that you can now use for experiments. So one of the experiments that people have proposed, or one of the models that people have proposed as a model of high TC materials, is the so-called Hubbard model. The Hubbard model is deceptively simple. It contains only two terms. One term is the hopping or tunneling energy from site to site, to nearest neighbors. This is constrained to tunnel only to nearest neighbors. And U corresponds to an on-site interaction. So if an atom hops, let's say this red atom hops from one site to a neighboring site, and interacts with the blue atom, that upspin and downspin atoms can interact and produce an on-site interaction U. So here's the kinetic energy, the tunneling, and here's the interaction energy, which occurs only if the two atoms are on the same site. If they're on different sites, they're assumed to not interact. So we're assuming only contact interaction. Because of Pauli's principle, there is only one red atom per site and only one blue atom per site, a maximum. You can't have two reds or two blues. Those violate the Pauli uncertainty principle, and they can't be both in the ground state. So we're excluding that configuration. This is equivalent to saying that we're looking at only the ground band of the optical lattice. So that's a very simple model, but yet it turns out that it may have all the ingredients for high TC, high temperature superconductivity, and we don't know yet. So what we're particularly able to do with cold atoms is to realize a Hamiltonian like this experimentally, and almost precisely be able to model at a tunneling rate and an on-site interaction rate, and have all the properties that we're expecting of the Hubbard model, but now with a very clean system and with tunable parameters. So this is a, I say here, a paradigm model of strongly correlated matter, but we don't know whether or not it contains high temperature superconductivity. It can't be solved. The interesting thing is the deceptive simplicity, I guess, of this Hamiltonian, in that it only has these two simple terms. Those two simple terms in a gigantic basis, where the size of the basis scales as 2 to the n. We were just thinking of spins that can be in one or the other spin projection. And so the basis scales exponentially with numbers of particles. So it can't be solved by classical computers unless you restrict the size, the number of particles, to a relatively small number, smaller than experimentally relevant in some cases. So the Hubbard model has some interesting phases of matter. One is called the Mott insulator, and it occurs when you have or very close to having just one atom, a density of just one atom per site. That's called half filling. And in that case, the Hamiltonian can be rewritten a little bit in terms of the Heisenberg model, in which there is some super exchange energy scale, call it J, which is the tunneling energy T squared divided by the on-site interaction U. That's the super exchange process. So it turns out that if temperature is less than U and tunneling is much less than U, then a Mott insulator develops at where there's exactly one atom per site, and that's called half filling, and this is kind of what it would look like. you have a bunch of downspin atoms in blue sprinkled over the lattice with a same number of upspin atoms that are shown in red. And they're kind of randomly distributed throughout this lattice with no magnetic order. It's an insulator because there's a gap called the Mott gap in energy that occurs right exactly at half filling. And the chemical potential lives inside that Mott gap, and there's no excitations. So what gets created like this remains like that. Atoms, don't flow, or electrons in a electronic material don't flow. They don't. There's no transport because everything is stuck into place due to these high on-site repulsive interactions that inhibit the tunneling. So this is shown here in the lower left. This is the calculations that are, I think, done by Asan Katami on some numerically linked NLSC. Maybe Teresa is there. She can tell me. I forget what it is, what the method is. But it's a method that enables you to calculate what the density profile would look like as a function of chemical potential or energy per particle. Let me move this thing away. All right, so here's the density on the vertical axis and the chemical potential scaled by U on the horizontal axis. And these are for different temperatures. So the red one is the lowest temperature. I'd like to focus on that. At a chemical potential of 0, the Mott gap begins to develop. And when the chemical potential increases to 1 in units of the on-site interaction, it begins to grow again. And this flat region is called the Mott gap. It's an energy region that is as wide as the on-site interaction strength U. And once the atom gets inside this Mott gap, it very much becomes an insulating state. There were some very nice experiments, both in Tillman and Esslinger's lab at ETH and in Emanuel Bloch's group in Munich, in which they demonstrated back in 2008 that a Fermi gas would manifest the Mott insulating state as a suppression of doublons, double occupied states, and also that it would be incompressible. The change in density with chemical potential would go to 0, reflecting this horizontal Mott gap. So there's a special case of this Heisenberg approximation to the Hubbard model, which is that the temperature at very low temperatures, temperatures that are less than this super exchange energy scale, which for us is of order tens of nanokelvin or so, the entropy per particle will drop below log 2. Log 2 is pertinent because it reflects the fact that the entropy is due to the spin degree of freedom, the particle being up or being down right at the Néel transition is essentially equal. And when you go below the Néel temperature, you're also going below the entropy of log 2 per particle. And so at that point, you become magnetically oriented. So you get, in a classical sense, up, down, up, down, up, down, checkerboard-like pattern. And you get a local moment, which reflects the fact that the spin states are projected into exactly all along Z or anti-aligned with the Z-axis. So this is shown here by this so-called local moment the magnetic moment squared divided by, or as a function of the chemical potential. So achieving this condition is quite challenging in optical lattice experiments, which for the following reasons. So this is a paper by Teresa Paiva back about 10 years ago now using quantum Monte Carlo, in which she showed that if you have a homogeneous gas, meaning not trapped, but rather uniform density profile, that the boundary between the antiferromagnetic mod insulator and the not magnetic mod insulator is given by this solid black line. And it's a convolution of two things. One, an exponential depending on T with respect to U, and the other having to do with the super exchange energy process. So at low interaction energy, this process dominates, and at high interaction energy, this one does. And you can see that there's a very gentle maximum where the antiferromagnetic order requires the least amount of momentum or entropy cooling. And as long as the entropy per particle drops below about 0.3 kb, you can get into this antiferromagnetic state. If you're at entropy per particle where the spin degree of freedom is random, you're pretty close to this brown line where the entropy per particle is close to 0.7. So in our experiment, we used two spin states of lithium-6 to be the stand-ins for the two different up and down spins of the electrons in a real electronic material. And these two levels of lithium-6 have a very nice Feshbach resonance in which the interaction is tunable over a wide range. And that's very convenient and very important for these experiments. So here's some typical parameters more for the expert. There's a lattice which has a depth of 7 recoil energies. This is the definition of the recoil energy. In lithium-6, it's about 1 microkelvin. This is the tunneling coefficient, T, at that lattice depth, and it's about 50 nanokelvin in energy, or about 1 kilohertz in frequency. The interaction energy is about 1/3 of the recoil energy. So, something about 10 times bigger than the tunneling. And the super exchange as a consequence is pretty much maximized at about 25 nanokelvin at this lattice depth. All right, so how do we deal with these requirements to get low entropy in this system? Well, we need to do some kind of evaporative cooling, because that's a way that the Bose-Einstein condensation was first observed. It's the way that we've gotten the lowest temperatures to study the BEC to BCS crossover in Fermi gases. And the way it works is the following. Imagine you have a collection of atoms in a potential that looks Gaussian like this one. If we set the filling of this trap, which is governed by this chemical potential mu, we set the filling to be very close to the lip of the trap. So in energy, this little energy gap is very small, and it could be adjustable just by changing the density or the parameters of the confining potential. And I'm imagining some kind of cross-beam trap, not a lattice. And you get very effective cooling where you can easily get below about 5% of the Fermi temperature. And that, in fact, is below the log 2 entropy scale that we had just looked at. So this looks very promising. However, if you look at an optical lattice, it's a very different beast than an optical trap. And in fact, the chemical potential for a half filling or a density of 1 is way down here at the bottom of the lattice. So here's the lattice, and the Gaussian-like envelope comes about from the confining envelope induced by the shape of the laser beam. So these laser beams are not infinite in extent. They have a finite extent governed by the Gaussian width of this potential. And so that Gaussian width determines where this chemical potential has to be to get in the right density. So there's no evaporative cooling. We're very far from being able to evaporate. And so in an optical lattice, it's a very different situation than it is in a crossbeam trap. So we realized that there was a way around this. So even though we can't adjust the chemical potential to be at the lip of the lattice, we can adjust the lattice potential to give effectively the same result. So here's the chemical potential again inside the lattice, but now we've compensated this confining envelope, this overall attractive Gaussian envelope, the shape of the laser beam. We've compensated it using anti-confining Flutie-tuned beams of light that are not retroreflected on themselves. So notice that the red light is retroreflected by this mirror, but the green light is not. This is what's called a dichroic mirror, which the green light is reflected away. So the result is that we can change where mu sits relative to the evaporation threshold, and just by adjusting this power of these anti-confining laser beams. So in doing that, we were able to realize a Mott insulator, a very nice depiction of the Mott insulator. The different colors, let's look on the right-hand side. These are symbols or data. The black symbols correspond to U of 3, the red ones to U of 11, and the blue ones to an even stronger on-site interaction of 14. And you can see by the time you get to 11 that there's a central plateau where the density is very, very constant at 1 per site. So this is a manifestation of the fact that this has become a Mott insulator, where there's now a Mott gap. And in fact, this area, this region where the density is fixed at 1 is very incompressible. The atoms don't like to move. And if you go up in density, eventually you come to a band insulator where there's 1 upspin and 1 downspin per site. This is what I was looking for, numerically linked cluster expansion. All right, so this is numerical calculations of the compressibility. The compressibility scales as the derivative of the density with respect to chemical potential. And this is along this axis is the density, number of atoms per lattice site. And when you achieve half filling, 1 atom per site, the compressibility vanishes. This is because it becomes an insulating state. And also, again, it vanishes when you have enough atoms to be in a band insulating state. This is exactly 2 atoms per site, and this is 1 atom per site. And so if you could measure the compressibility by measuring the change in density with respect to numbers of atoms, you can compare directly with these calculations. So that's what we've done here. This is a paper whose first author was Pedro Duarte, experimentalist in my group. And the theory was, I think, done by Jason and Teresa. And you can see that that as you go up in U, there is the first minimum, which is due to the fact that this is a mod insulator, and the compressibility vanishes in the insulating state. And the comparisons are comparisons with theory. So that's the mod insulating state. That's the precursor to the antiferromagnetic order. But to get to see antiferromagnetic order, you have to go to even lower temperatures, as I mentioned, to temperatures that are near the super exchange energy scale, if you want to see something with very long-range correlation. So the way we can measure the correlations is to use Bragg scattering of light. And so here's our crystal lattice shown in 2 dimensions. It's actually 3. But you have light incident on this lattice at a certain angle, the Bragg angle. And if there is correlations that have developed, there are correlations, you will see light scattered coherently at a particular angle. And the Q equals pi angle refers to the lattice vectors that one needs to match via this relationship, the Bragg condition, to match Q with the incoming wave vector determined by this incident light. And once you do that, then you get coherently scattered light that this red vector is represented here as being either scattered light from the upspins or in blue from the downspins. This is what the experiment looks like. There's an ultra-high vacuum chamber. We then send in light at the Bragg angle, and we look at the corresponding Bragg angle. I guess the light comes in this port. And we look at the coherently scattered light on this camera. And we also put a camera on a random angle. We call that random angle theta. And we expect to see coherently scattered light coming in this direction, and only diffuse scattered light coming in this direction. And that's the Bragg condition. So the Bragg condition turns out to be achieved with this wavelength of light at 57 degrees. And it can be spin sensitive. So it looks a lot like X-ray scattering, except it's actually more like neutron scattering. This neutron scattering is spin sensitive. And we can make this scattering to be spin sensitive by detuning halfway between what we call the upspin atoms in red and the downspin atoms in blue. So if we're detuned to the red for the blue atoms and to the blue for the red atoms, a little bit confusing, but more energetic beam for the probing the upspins than the down, then one gets a phase shift in the scattering. And that phase shift allows you to distinguish the spin-dependent scattering function. So that function is called the spin structure factor. This is the static structure factor. It's for elastic scattering. This is the Q is the Bragg wave vector. And we're looking to see a non-zero value of this correlation function, and which occurs once you get close to the nail temperature and antiferromagnetic order is supposed to develop. So it turns out the Bragg signal is proportional to this static structure factor. And you can measure the fraction of light which is scattered back into this camera. You can determine what the correlations are in this system. And you can normalize it. You don't have to know exactly, calculate exactly what the transmissions of the windows and all of that. You can simply normalize by the intensity of light coming out at the particular Bragg angle after long times of flight, after you remove them from the lattice. So that's our normalization. So in fact, this is a proportionality, but these are equalities. So one just needs to make two measurements. So this is a calculation that shows the static structure factor as a function of density or doping. And so, of course, in our experiment, we vary the number of atoms to be near this half filling point where the correlations are maximum. And these correspond, these different colors, to different temperatures. So you can see how sharply the correlations are dependent upon the temperature. So this temperature range shown from blue to black is a factor only of 2.5 in temperature, but yet it's probably an order of magnitude in peak height. So this is in fact what we saw. This is the absolute magnitude of that spin structure factor versus interaction strength U over T. So this in fact looks a lot like Therese's calculation with quantum Monte Carlo, in that there's this nice maximum at around U over T of about 11 or 12, something like that. And so that actually matches the theory pretty well. It's shown here for the different colored lines, or the theory lines corresponding to different temperatures. And if you look closely at the data, you can see that it matches the dark green temperature the best, temperature of about 0.5 in units of the hopping. And the fit is really, I think, remarkable, that it fits almost exactly on this line. So this is an excellent thermometer, the combination of the experiment and the theory, in this range where quantum Monte Carlo still works. But I'm told, at least I was when this work was done, that this was about the limit of the quantum Monte Carlo that was limited by this computing power. And it was, taking months, I guess, to make this calculation. So the temperature is about 0.5 in units of the hopping. And it's known, though, from the theory that the transition temperature is around 0.37, I think it is. And we're at about 0.5. And so we're above the nail transition, but not so far above it that we don't already see the development of magnetic correlation. So there are magnetic correlations that are happening. They're just at a region which is a little bit lower down on this plot, very close to the green peak. And we would like to be at the nail transition, which is very close to this blue one. So how do we get colder? Well, Therese's work from a decade ago kind of shows this. Remember the graph, I showed this earlier, in the homogeneous case where the density is homogeneous. And you needed to get the entropies below 0.3 per particle. But if you take advantage of inhomogeneity, then the peak region and the Mott plateau gives you a way of minimizing entropy locally, and where all the excess entropy resides in the wings of the distribution. So this is the case where the atoms are trapped in a harmonic potential. And now instead of 0.3, we only require 0.65. So just right at basically the log 2 for the restricted region of space that you're in the high density region. So the bottom line of this is that entropy is stored in the wings. The reason this works is that the entropy is stored where the density is small, so they're metallic. And the conclusion is that total entropy is conserved, but you can redistribute it. So you can have less entropy in the center of the trap and more entropy out in the wing. And this is something that Marcus Greiner actually realized in his quantum gas microscope experiment, where they used a square lattice, just a single two-dimensional plane, and they have on-site resolution, so they can observe single atoms and detect the whether the atom is an upspin or a downspin. So they were actually able to see correlations that extended much further out. This is in numbers of sites. Our correlations were about 1 atom per site. And you can see they're seeing correlations that extend out to something like 8 atoms or so. And so their atom structure factor turns out to be really high at these particular lattice directions. Okay, so in summary, these are examples, I think, of quantum simulation of non-trivial Hamiltonians with ultra-cold atoms and lattices, in which we can study very pristine realized models, such as the BEC-BCS crossover, such as spin imbalance Fermi gases, and as I've shown here today, with antiferromagnetic order in the Hubbard model. So we'd like to be able to get colder in our apparatus, and so we're going to adopt some of these ideas that arose from Teresa's paper, that you can store entropy in low densities in the wings in a reservoir, and realize lower entropy in that case in the center of the trap. So the temperature is a problem because we're at the limit of QMC, quantum Monte Carlo. So that's as you go away from half filling, you're limited by what they call the sign problem. It has to do with the Pauli statistic. And the Heisenberg model is, once you go away from half filling, the Heisenberg model is no longer any good. So we're in the limit of what we can do in terms of thermometry for a doped system. So let me acknowledge the people who did this work. Experimentally, it was Pedro and Russ Hart and Ernie Young. And experimentally, David Hughes, Nandini Trivedi, Richard Skolatar, Teresa Paiva, and Ehsan Khatami. So thank you. And let me advertise my third lecture tomorrow. I think it's tomorrow morning at some point, at least morning in my time. And I'll talk about the physics of fermions in one dimension that are realized using a two-dimensional optical lattice that produces a bundle of one-dimensional tubes. And these one-dimensional tubes enable you to realize some very fundamental models of strong correlation physics that occur in low dimension. All right, thank you.
Thank you, Randy. So, do we have some questions? Comments, please come up. Please come over. Yeah, he's gonna ask you about the first lecture, but no matter.
Good afternoon. Where is the camera?
Hi.
Hi. I have a question actually already from the previous lecture. I tried to think about it, but I didn't arrive really at a conclusion. Can I ask it?
Sure.
Okay. So you said in the previous session that if you have an attractive effective potential, you cannot have in a free system Bose-Einstein condensation. But then if you put a trap, then this is possible. Now, if I understand correctly, this comes from the fact that in the free space, the bosons are going to collapse. But this is not anymore the case when there is the trap. And I don't understand, well, if you can give me an intuition how including a trap would prevent this collapse and how the repulsion, I guess, emerges.
Yeah. Okay. It's just yeah. The explanation for that is that you have 0-point energy in a trap, and the collapse process occurs when the chemical potential is equal to this h bar omega, the separation between a higher order radial trap level. And so once the chemical potential gets big enough and you start mixing in more than one level of the trap, you'll have a collapse.
Okay, but then when if you release the trap, so you make the trap larger, then you expect that this is not anymore the case and you don't have the condensation anymore.
That's right.
I see.
If there's no 0-point energy, then all of the radial confinement, it's not, if it's an infinite extent, all those levels are degenerate.
Okay, thank you.
Thank you. Any other questions? Vanderlei?
Hi, Randy.
Hi, Vanderlei.
I cannot resist because asking what I'm going to ask you. This is a school, and I think everybody learned magnetism since undergraduate. And my question to you is, what new ideas can we come with simulating the magnetism in those cold arm samples? If you want to give an advice to anybody that are excited about magnetism, what will be the challenge to overcome?
Yeah, okay. Great question. So the magnetism seems to underlie superconductivity in these unconventional superconductors. It seems to be the case that every high TC material we know, or certainly most, have this phase somewhere near the superconducting region of the phase diagram. So there is something about antiferromagnetic order which is important to the way that these materials become superconductors. And so the motivation is to understand the Hubbard model and all of its regions in the phase diagram of doping versus temperature, but also to understand if there is some connection between superconductivity and magnetism, how we can exploit that connection to make even higher temperature superconductors. So, you know, the world was pretty shocked, I guess, in 1985 when these high temperature materials were first seen and made. And, you know, very quickly the critical temperature increased very rapidly in a matter of, you know, weeks. And we went from critical temperatures that were like maximum 10 or 15 degrees Kelvin to temperatures that were 150 degrees Kelvin. So, you know, there is something very significant about magnetism and something that may enable us to make better superconductors.
Okay. Any more questions? Comments? Teresa, please.
Oh, he's here.
Jeez.
Hi, Randy.
Hi, Teresa.
Long time no see.
I know.
Yeah. So I'm not going to do as van der Leyen ask why study magnetism, because it's fun and because we learn a lot from it. But I'm really curious, like, to know, where are you headed? So what's next for you? What experiments are you going to do in your lab?
Yeah. So we're really been focused on one-dimensional physics in the last few years. We have a paper on the archive right now that I'm very excited about, which is the spin charge separation, that phenomena that one can see in a one-dimensional Fermi gas. And we're ultimately would like to make a P-wave superconductor in one dimension. You know, as far as anybody knows, there is, you know, as far as been rigorously proven, I guess I would say, there are no P-wave superconductors. And, you know, why is that? I don't really understand that there's a good reason for this. Furthermore, a P-wave superconductor in one dimension is a realization of the Kitaev model that is predicted to harbor Majorana fermions at the ends of a one-dimensional wire. So this would, Microsoft, for example, is trying to exploit these Majorana fermions topological excitations to make a topological quantum computer. And so if we could help by seeing what ingredients are necessary to see a P-wave superconductor, we might be able to help realize the potential of these systems to be topological.
Great, Andy. Do you want to? Okay. So, very interesting physics and experiments. Though we do have a time schedule here, and I apologize, but I'll have to finish the session, okay? Thank you very much.
My pleasure.
And hope to continue this collaboration anytime soon, okay?
Likewise. Great to see you all.
Take care.
I guess I'll see you tomorrow.
Let's thank Professor Hulet again.
Thank you.
Here we go. Now we go for the coffee break, please. The ones.